Welcome to this lecture, first order systems. The liquid level in a tank. The tank through which a liquid flows continuously in and out is a first order system. It's an example of a first order system. The background information, the information about this process happening here and the relationship between the flow and the head have been described in my previous class lecture titled as PC47, PC47. Now we will see what process, what equations describe this process, and based on that we will arrive at the transfer function of this tank and show that it is first order. So these are the variables. Q and Q naught are the volumetric flow rates of the liquid flowing through this tank. Q is at the inlet, Q naught is at the outlet. H is the height of the liquid at any time in the tank. R is the resistance at the outlet, and the tank has a uniform area of cross section. The tank's area of cross section is uniform and it is denoted by A. In the last lecture, PC47, the flow head relationships, different types are being described. So now we will assume that the flow head relationship is linear. That means this Q naught equal to H by R. So this is the assumption with which we are going to describe this process and find out which equation describes this process. So first you make an unsteady state mass balance. Mass in, input equal to output plus accumulation. So mass in is rho into Q. Rho is the density of the liquid. Rho is the density of the liquid. Q is a volumetric flow rate. So mass flow rate is rho into Q at the inlet. At the outlet, it's the same, rho into Q naught. And accumulation is d by dt of the mass which is stored in the liquid in the tank at any time. The mass of the liquid stored in the tank at any time is volume into density. Volume is area into H. So the mass is area into H into rho, AH rho. So d by dt of AH rho. So A and rho are constants. We'll assume that density of the liquid also constant. Area is uniform area of cross section, so constant. So that is equal to rho Q naught plus A rho dH by dt. So this is the unsteady state mass balance. So this equation describes the process during unsteady state. Now if you cancel rho throughout, you get this equation 3. You get this equation 3. Now we will substitute our flow head relationship into this, where into Q naught. For Q naught, I'll substitute H equal to dH by Q naught equal to H by R. I'll substitute here. I'll substitute Q naught equal to H by R. That is equation 1. I'll substitute for this. Now if I substitute Q equal to H by R plus A dH by dt. Okay, now we'll go to steady state mass balance. So steady state mass balance is the same, mass in equal to mass out, only thing mass accumulation will be 0. So at steady state, mass in, rate of mass in equal to rate of mass out. So that is equal to, you can write with rho Qs equal to rho into Q naught S, rho and rho cancel. So Qs equal to Q naught S. Once again, I'll substitute equation 1 for Q naught. Q naught equal to, equation 1 is Q naught equal to H by R. At steady state, the variables are denoted with the subscript S. Okay, the variables are denoted with the subscript S. That is our usual notation. So at steady state, this equation becomes Q naught S equal to HS by R. So that is what is substituted here. Instead of Q naught S, HS by R is substituted. So this equation becomes, instead of Q naught S, I substituted HS by R. So this is equation 6 at steady state. Now you have an unsteady state equation, equation number 4, and you have a steady state equation, equation number 6. So subtract these two equations, steady state equation 4 minus 6. 4 minus 6 is going to give you q minus qs on the left hand side, right hand side h minus hs by r, and a dh by dt. Now this is q minus qs, this is h minus hs, this is dh. I can make this also as d of h minus hs, because steady state value hs is a constant. All these s subscripted variables are constants, qs and hs. So I will modify this dh by dt as d of h minus hs, just modified. Okay. So after modifying dh by dt as d of h minus hs, you get this equation 8. Now let me introduce the deviation variables. Deviation variables q minus qs equal to capital Q, which will be a function of time. So h minus hs equal to capital H, that also will be a function of time. So I'll introduce these variables and substitute in equation 8. Substitute these deviation variables in equation 8. So this becomes capital Q, this becomes capital H, and this becomes a into capital dh by dt. So you get a first order differential equation, first order linear differential, first order ordinary linear differential equation. So it is this equation which describes the process happening in the tank. Process is simple. Liquid is flowing through the tank, and the outlet flow is the driving force for the outlet flow. There is no external driving flow. It is only the liquid head. The liquid head is the driving flow for the outlet flow rate. So the process is described by this first order linear ordinary differential equation. Well, now how do you get the transfer function from this equation? From a differential equation, how do you get a transfer function? Take Laplace transform. Take Laplace transform. H of t, Laplace transform is H of s by r, and this is first order, sorry, this is a differential equation, is a first order derivative, is a first order derivative, first derivative. So Laplace transform of this is s into h of s minus h0, right? Now this h0, capital H means deviation variable, h minus hs. At h0 means evaluated at t equal to 0. At t equal to 0, the initial time, there is no change. It is at steady state. So the change happens at 0 and it starts varying after 0. So at 0, h is equal to hs, or the deviation variable capital H is 0. The deviation variable is 0 at 0 time, h0 equal to 0. So if you cancel out this and take simplify other terms, what do you get? Q of s, here I take an h of s common, so 1 by r plus as. So this term is 0, this term is 0, sorry, this is 0. So remaining terms are this. So you can see this simplification, simple rearrangement. And if you rearrange and take hs by qs, you are getting r by ars plus 1. You are getting r by ars plus 1. And this is of the form k by tau s plus 1, is it not? This is of the form k by tau s plus 1, which is first order. K is called what? K is a gain. Here k is equal to r. K equal to r. The gain equal to r. R is nothing but the resistance. And tau, what is tau? Time constant. Time constant equal to a into r. Area into resistance is the time constant. So you get h by q equal to r. R by tau s plus 1 or k by tau s plus 1 is the form, standard form, k by tau s plus 1, k equal to r and tau equal to ar. So this is a transfer function relating the height and the inlet flow rate. Height and the inlet flow rate. When you give a change in Q, when there is a change in Q and there is a disturbance in Q, H gets disturbed. H also changes. So what is the relation in terms of transfer function between H and Q? Between H and Q is what we have derived. Hs by Q is equal to K by tau s plus 1. K is R and tau equal to AR. Now there is also another transfer function relating Q and Q naught. Because if there is a change in Q, not only H changes, but Q or Q naught also will change. So there is a transfer function relating Q, inlet flow rate and outlet flow rate. How do we get this? Equation 1, our assumption is Q naught equal to H by R. At steady state, this equation becomes Q naught S equal to Hs by R. So if you subtract this, Q naught minus Q naught S equal to H minus Hs by R. And introduce deviation variables. Q naught minus Q naught S is capital Q naught and this is capital H. Now take Laplace transform of this. Take Laplace transform of this, you get Q naught S equal to Hs by R, or Hs equal to R into Q naught S. So you substitute this in equation 12, which is equation 12, this. So in this, for Hs, we substitute R into Q naught S. For Hs, we substitute R into Q naught S. So if you substitute this, you find that this R on right hand side R cancels. So you get Q naught S by Qs equal to 1 by ARs plus 1. That is of the form 1 by tau s plus 1. So here you find the gain is 1. K is 1 here. The gain in the numerator is 1 here. And tau is the same as before, AR. So these are the two transfer functions in the tank. One relating the height and the inlet flow rate. The second one, this one, relating the outlet volumetric flow rate and inlet volumetric flow rate. So here, the gain is numerator is 1. You find because this relates both the volumetric flow rates, the left hand side. So there is no dimension of this gain, because it relates, the dimension of this gain depends on what it relates, the Q naught by Q. So Q naught by Q, both are same units, no dimension net. So this gain also has no dimension, it is simply 1. Whereas in the previous case, this function K has got units, K equal to R, and this has got unit, that is nothing but the conversion of Q to H. That is, the units of R will be the same as height by flow rate. Units of K, which is nothing but R here, the dimensions of that will be height divided by volumetric flow rate. So these are the two transfer functions, number 1 relating Q and H, and number 2 relating Q and Q naught. We'll discuss more in the next lecture. Stay in touch. See you.